Alright, today is 11th of January and this is the second part in the discussion of linear regressions. So we have ended in full information maximum likelihood estimation. We will begin with identification. The set of first order conditions mentioned earlier is a system of 5 equations and 5 unknown identification problems. Is the issue of if there exists a unique solution. There are two conditions for identification. First of all, order condition. Order condition is when number of equations is more or greater than number of unknown parameters. Rank condition. In rank condition, the Jacobian equivalent to Hessian equivalent to information matrix must be non-singular. So the Hessian or the information matrix, as we know, they must be non-singular. They cannot be singular. Mostly you need to be able to estimate Hessian and information matrix as well as Jacobian. Otherwise, Kolesky decomposition, if they must be inversible. Otherwise, the Kolesky decomposition will not work. If they are singular, that means there are multicollinearity in the values of the parameters with the residual. So as we already know, phi equals minus a by b, and the expected value of omega and omega transpose is equal to just the decomposition, which is v inverse v inverse transpose. The dimension of these parameters are as follows. The reduced form of phi is n by k plus 1. Who was n by k? As we can recall, the a coefficient was n by k, phi is n by k plus 1, and hence the expected value of v and v transpose, the correlation between them is n int n plus 1 divided by 2. Structural form, a is n by k plus 1, so v omega is n int n plus 1 by 2. B on the other hand is a square matrix n by n. So phi and A is rectangular matrices and B is a square matrix. The total number of parameters in the reduced form is n into k plus 1 plus n into n plus 1 divided by 2. Well, so the total number is estimated with taking the size of phi or A, and add this up with the dimension of a variance covariance matrix n into n plus 1 by 2. Well, the structural system has at most n square plus n k plus 1 plus n into n plus 1 by 2 parameters, means there is potentially n into k plus 1 n square plus n into k plus 1 plus n into n plus 1 by 2 minus, so the maximum parameters minus the n into k plus 1 plus n into n plus 1 by 2, the reduced form parameters. Maximum parameters minus the reduced form parameters leaves you with n square only. More parameters in structural form, we need to reduce n square. So there is n square more parameters in structural form than reduced form. So we need to basically, so the first part is the dimension of the structural form, and the second part is the dimension, or first part is the total number of parameters in structural form, second part is the total number of parameters in the reduced form. So I have n square more parameters in structural form. We need to reduce n square with normalization. My normalization is putting n square minus n restrictions on the dependent variable. For example, 0 restrictions, cross equation restrictions, restriction on covariance matrix of disturbances. Very important, or covariance very important for structural vector to regression models, that is done in chapter 13. This is how we recover reduced form from structural form with restrictions, number of restrictions imposed, and generally the restrictions is equal to the size of the excess of in structural form compared to the reduced form. Example 5.10, identification in a bivariate simultaneous system. So B is already known to us, which is 1 minus B1 minus B2 1, A is 0 minus alpha. V is a diagonal matrix, variance covariance matrix is a diagonal matrix. Phi is already known to us, minus A by B. You put in the values of A by B, you are left with alpha B1 divided by 1 minus B1 B2 and alpha divided by 1 minus B1 B2, and 3 unique solutions obtained from the covariance restrictions from here. So expected value of omega and omega transpose is the variance, the decomposition, which is B inverse transpose multiplied to the omega. So B inverse transpose multiplied to the omega, or you can put in the values of B, which is 1 minus B1 minus B2 1 inverse omega is, as we all know, the diagonal matrix, sigma 1 1 sigma 2 2 0 0, and again putting the values of B, and then we just multiply them and we are left with this particular equation, gamma 1 1 beta 1 square gamma 2 2 1 minus b1 b2. So 1 minus b1 b2 whole square is common in everyone. Gamma 1 1 b1 square gamma 2 2 gamma 2 2 b2 square gamma 1 1 b2 gamma 1 1 b1 gamma 2 2. Very simple. So number of equations here is 5, which equals to number of unknowns. So you have how many equations here? 1 2 3 1 2 3 4 5, which is equal to the number of unknowns here. 1 2 3 4 5, fifth one is alpha, isn't it? Yeah, which is order conditions are here, order conditions are satisfied. So number of unknowns means number of parameters that we need to estimate. If number of equations are exactly equal to the number of parameters, then order conditions are satisfied. So a just identified number identified in a just identified system, the reduced form equals to the structural form, which means number of parameters equals to the number of unknowns, or basically the reduced number of parameters in the reduced form equals to the number of parameters in the structural form. In a over identified system, the number of parameters in the reduced form is higher than the number of parameters in the structural form. In the under identified system, the number of parameters in the reduced form is less than the number of parameters in the structural form. And for an under identified system, the Jacobian becomes a singular, so we cannot solve it. Decomposition does not run, the solution does not exist. In another way to explain is, in a just identified system, number of parameters equal to the number of equations. In over identified system, number of equations, number of parameters are in an over identified system, number of parameters are more than the number of equations. In an under identified system, number of parameters are less than the number of equations. Generally number of parameters. If more than the number of equations is still executable. If number of parameters are less than the number of equations is not. Okay, moving on to instrumental variables. We already did some mathematics with instrumental variables. Another method of estimation, the OLS of beta from y1t and y2t is, so we are familiar with this equation, b1 y2t, b2 y1t. With in the second equation we have the dependent variable to be a function of dependent variable and an exogenous variable. In the first equation, the dependent variable is only a function of another dependent variable. So obtaining by ignoring the second equation in the system, the OLS is beta 1 hat equals y1t y2t divided by y2t y1t. However, this is not a consistent estimator of beta 1 because the expected value of y2t, basically the covariance of y2t with the residual is not equals to 0. So here y2t is correlated with u1t, so because it's not equals to 0, and their covariance is not equals to 0, so this is not a consistent estimator, that is multicollinearity. FIML of beta 1, on the other hand, because OLS is not a consistent estimator, there is inconsistency. FIM y2t equal is correlated with u1t. FIML of beta 1 is y1t xt divided by c, y1t y2t y2t y1t, but FIML is y1t xt y2t xt. It's a consistent estimator. This estimator is also known as the instrumental variable estimator because xt not included in y as an exogenous variable. Xt is not included in y as an exogenous variable, but xt is a perfect instrument for y2t. Xt corrects the dependence between u1t and y2t. So this is the instrument for y2t, and it corrects the dependence of the correlation between y1t and y2t. So it's a consistent estimator because xt is the instrumental variable. A quick way to see this is when we take expectation of y1t and xt, which equals beta 1 expected value expectation of y2t, basically just the covariance of y1t with xt equals beta 1 multiplied to the variance covariance of y2t xt plus residual u1t xt. So let's solve for beta 1. Solving for beta 1, we have y1t xt variance covariance divided by y2t xt variance covariance, which is almost because u1t xt is 0, variance covariance of u1t xt is 0. Obviously u1t xt will be 0 because in first equation xt is not there, so xt is not correlated with u1t, it's correlated with u2t. So beta 1 is equivalent to which is the beta estimation, beta parameter estimation of instrumental variable technique, that equals to that, which is also equals to the beta parameter estimation with FIML technique. So this is a consistent estimator, kindly proved. Rearranging the first order conditions with respect to beta 2 and alpha 1. So we take the first order condition in this equation and rearranging, we have y1t summation of y1t minus beta hat y2t, beta 1 hat y2t multiplied to the exogenous variable or the instrumental variable instrument to estimate beta hat xt equals 0, or y2t minus beta hat to y1t multiplied to the error term u1t equals 0, or this can be rewritten as, without taking u1t, this can be rewritten as y2t minus beta 2 y1t minus alpha hat xt multiplied to the instrumental variable xt, which also equals 0. Properties. Instruments are correlated with variables. They are instrumentally distributed. Instruments are correlated. So instruments are generally correlated with variables. Instruments are uncorrelated with disturbance terms. So that's an important property, because instruments are correlated with variable means instruments take away multicollinearity from the variables that the variables have with the residuals, and they're generally uncorrelated with residuals. Moreover, they're asymptotically normal. If the distribution is not asymptotically normal, it is known as the instruments distribution is generally asymptotically normal. If the distribution is not asymptotically normal, they're known as the weak instruments. Weak instruments. Now let's talk about weak instruments. So the first equation, u1t equals beta 1 y y1t beta 1 y2t plus u1t y2t alpha xt plus u2t. So in the first equation, the dependent variable is a function of dependent variable itself, while in the second equation, the second dependent variable y2t is a function of an exogenous variable here. So y2t equals alpha xt plus u2t, but there is no u1t here, so basically it's a weak instrument. Here ut is IID with 0 mean and sigma variance. Basically sigma square variance represented in this manner. Here the value of sigma 1 2 controls the strength of simultaneity bias. So the parameter values, sigma 1 2 equals 0, which is OLS of y1t, which is estimated with the OLS of y1t on y2t, which results in an asymptotically normal b beta. Alpha equals 0, as the correlation of y2t with xt is 0. xt, in that case, if alpha equals 0, then xt is not a valid instrument, because xt must be correlated with the variable y2t. There must be positive values. So when alpha, obviously if alpha becomes 0, then xt is not a valid instrument. Beta equals 0, meaning the instrumental variable mean is located at the mean of the instrumental variable is located at the true population mean, which is nice, which is more desirable when beta equals 0. If alpha is less than sigma 2 2, so we talked about sigma 1 2, which is estimated with the OLS of y1t on y2t. If alpha is less than sigma 2 2, weak instrument, we have weak instrument here. Is a evidence of weak instrument. If alpha goes up, quality which increases compared to sigma 2 2, when sigma 2 2 remains constant, quality of the instrument is getting better. So the properties, If k equals number of instruments, m is equals number of variables that require instrumenting. So k is number of x's, m is number of y's. Model is just identified when you have k equals m or number of y's equals number of x's. Over identified when you have k more than m, k is greater than m, that means you have more x's than y's. Under identified when k is less than m, when you have less x's than y's. If X is a T by K rectangular matrix with K instruments, Y1 is a T by M matrix of rectangular matrix of dependent variables. Y2 is T by M rectangular matrix of M variables that are to be instrumented. So basically not all y's, we are talking about y2 and x, not y1, because y1 is dependent variable. Beautiful. So the instrumental variable estimator of a single equation, see, we used this equation yesterday in our problem. So y2 prime, y2 transpose x, x transpose x inverse, x2 x transpose y2 inverse, then y2 transpose x, x transpose x inverse, then x transpose y1. Yesterday what we used, instead of y1, in one case we used w and we used y2. Beautiful. And the covariance matrix, we also use this, the covariance of parameter of the instrumental variable is sigma hat square variance divided by y2 transpose x, x transpose x inverse, x transpose y2. Beautiful. So to devise the instrumental variable estimator of a single equation is y2 transpose x, x transpose x inverse, x transpose y2, then y2 transpose x, x transpose x inverse, then x transpose y1. And the covariance of the instrumental variable parameter is sigma hat square estimated variance covariance matrix divided by y2 transpose x, x transpose x inverse, and x transpose y2. Now sigma hat square is residual variance in case of just identified model. So it's the variance of the residual in case of a just identified model when you have number of y2 equals number of x's, which is the case we have here. So the instrumental variable becomes x transpose y1 divided by x transpose y2 for multiple regression parameters. For example, in case of modeling contagion, when you have returns on two asset markets, y1t and y2t, so y1t y2t, then alpha 1 y1t minus 1, which is the lag of y1t, then alpha 2 is dummy variable representing an outlier in the returns of ith asset, d1t alpha 3. So there are two dummy variables, one is representing an outlier d1 and d2t is representing in the returns of ith asset. No, basically they're both dummy variables representing an outlier in the returns of ith asset. They are just dummy variables, that's all. So alpha 2 d1t, alpha 3 d2t plus u1t, y2t is beta 2 y1t, alpha 4 y2t minus 1 is the lag, and with dummy variables alpha 5 d1t, alpha 6 d2t plus u2t. Basically when you are representing dummy variables one dummy variable, I guess, is representing the dummy variable vector for y1t, and another one is representing dummy variable vector for y2t. That's all. Yeah, that makes sense. So null is alpha 3 equals 0 in just identified model. Alpha 3 if equals 0, then this becomes, the dummy variable becomes 0. Autocorrelation in returns is small, so weak instrument problem. The autocorrelation is represented with sigma 1 2 divided by root over sigma 1 1 sigma 2 2. Very easy. Sigma 1 2 divided by root over sigma 1 1 sigma 2 2. So the diagonal elements are on the denominator under the square root, and non-diagonal element, the common non-diagonal element, is on the numerator. That's all. So this is instrumental variable. Then we are talking about seemingly unrelated regression. So basically, a seemingly unrelated regression or SUR models is a simultaneous equation modeling system where each dependent variable only occurs in one equation. So structural coefficient matrix V is a square n by n identity matrix. For example, there is a trivariate seemingly unrelated regression model, which is y1t equals alpha 1 x1t plus u1t. Here the dependent variable is a function of exogenous variable, it's not a function of other dependent variables, unlike before. y2t equals alpha 2 x2t plus u2t, y3t equals alpha 3 x3t plus u3t. So there are trivariate SUR models. u1t equals ut equals u1t, u2t, u3t has the properties ut, which is IID with n zero mean and sigma variance. In matrix notation, the system is yt plus axt equals ut. Yt plus axt equals ut. A is nothing. You just take all these three equations to your left hand side, and you have minus alpha 2, minus alpha 3. You just name them A. That's all. Put them in a matrix. So alpha is diagonal. It takes a diagonal shape. Minus alpha 1 0 0 0, minus alpha 2 0 0 0, minus alpha 3, as you can see. Yt is y1t, y2t, y3t. Xt is x1t, x2t, x3t. It's a very simple structure. The log likelihood function of this seemingly unrelated regression is minus n by 2 log twice pi minus n by 2 log of determinant of absolute value of v, or here I think it's just omega, yeah, minus 1 by 2t multiplied to the decomposition, which is first the y1 plus axt transpose v transpose multiplied to yt plus axt. That's all. Is just the decomposition, just like before, nothing new. With n is equal to 3, number of observations equals 3, this expression is maximized by differentiating log likelihood with respect to parameters alpha 1, alpha 2, alpha 3. So number of unknowns are much more, which is alpha 1, alpha 2, alpha 3. Then you have the elements from variance covariance matrix: sigma 1 1, sigma 2 1, sigma 2 2, sigma 3 1, sigma 3 2, sigma 3 3, because you have three systems of equations. Yeah, makes sense. And setting these derivatives to 0 to find theta hat obviously is first order condition. Example, equivalence of seemingly unrelated regression and least square is represented with so the equivalence of seemingly unrelated regression and least square estimates are considered the class of seemingly unrelated regression models where independent variables are the same in each equation, and u1 y1 equals alpha 1 xt plus ut, in which residual ut equals u1t u2t up until is a residual ut is the error vector, is IID 0 mean and v standard deviation, and a is minus alpha 1 minus alpha 2 to minus alpha n that we have already seen. Estimation of maximum likelihood estimator yields same results as well as estimates on each equation. So only if independent variables are same in each equation. Which means that alpha 1, alpha 2 to alpha n should equal. The estimation of MLE yields same result as well as estimates on in each equation. Then we need to test LR, Wald and LM. Then there's one problem. Single equation model. Now we are given some examples. Single equation model. Well, yt equals beta naught plus beta 1 x1t plus beta 2 x2t plus ut, which is IID n0 sigma square. You have theta parameters given to you, which is beta naught, beta 1, beta 2 sigma square, and x1 to x2t is IID n0 and identity matrix, and the matrix is identity matrix. T equals 200. Null is while jointly beta 1 and beta 2 is jointly 1, which is basically meaning that whether they are jointly a uniform distribution or not. By imposing beta 1 plus beta 2 equals 1 restriction, imposing restriction, the restricted MLE parameters are estimated from the model. Y equals beta naught t plus beta 1 x1 t plus 1 minus, because with the restriction, 1 minus beta 1 x2t plus ut. The likelihood ratio test is now unrestricted parameter minus the restricted parameter. We have already done that previously. Is chi-square under null hypothesis based on the assumption of normal distribution for the residual, and alternative form for likelihood ratio statistics for a single equation model is t log of sigma naught square minus sigma 1 square. So instead of finding the unrestricted and restricted theta parameters, we can just take the difference of sigma naught, which is the, I think, the variance covariance matrix of the restricted, minus the unrestricted minus the variance covariance matrix of the restricted. The difference 1 and 2 is the same value, so either you can take all the parameters or you can simply take the variance covariance matrix. In this example, the PV, the probability value, is 0.59792, showing restriction is not rejected at 5% level. So 0.5972 is not rejected. It would have been rejected at 0.5% if it was below 0.05. Yeah, so it's 0.5, which is not rejected, about 59% significance. To compute Wald statistics now, it's very simple. R equals 0, 1, 1, 0, Q equals 1. Why 2 ones? Because they are like simple. Beta 1 plus beta 2 equals 1. So 1 minus, well, for each one you put 1 restriction. 0, 1, 1, 0, q1 and compute negative Hessian matrix. The world statistics is then r theta 1 minus q t r theta 1 minus q transpose, or negative Hessian theta r transpose inverse multiplied to r theta 1 minus q transpose. I think we did this math before. Yeah. 1, 2 and 3. The Allen statistics require evaluating the gradients of unrestricted model at restricted estimates. Gradients of unrestricted model at restricted estimates and compute outer product of the gradients. So t, the inverse of the gradient of theta naught is unrestricted parameter theta's gradient, inverse of the OPG or Jacobian theta naught, and again the gradient of unrestricted parameter. So J inverse equals to negative information is information matrix inverse 2, which is information matrix is a inverse here is equals to negative Hessian. Now that's something we always need to remember. Negative Hessian inverse. So that is chi-square. The form of LR Walt and LM for multiple equation is same as single equation. For multiple equations, we have n by 2, the parameter log theta is n by 2 log twice pi minus half log determinant of omega plus log determinant of b. In both cases they are absolute values, minus 1 by 2t byt plus axt transpose. We are familiar with this, we did this before. V inverse and vyt plus asterisk. The unrestricted MLE, maximum likelihood estimator of V, is, well, ut transpose divided by t, and residual ut is beta 1 by t plus axt. This is also coming from the reduced form equation. The log likelihood function for unrestricted estimator is log likelihood of theta 1. Well, I think I made a bit of mistake here. This is restricted theta naught, this is theta 1 is unrestricted. Okay, so unrestricted parameter, the log likelihood of unrestricted parameter is unrestricted estimator is log theta 1 minus n by 2 log twice pi half. Same thing. There's nothing. Is there any changes? No, there is not a single change. 1 by 2 log twice pi 1 plus log twice pi. Alright, using the result from chapter 4 in case of unrestricted estimator, when the decomposition portion, the decomposition element equals 1, in that case decomposition element becomes n. In that case, if the whole thing here becomes n, n by 2 1 plus log twice pi, so basically that leaves you with n by 2. N by 2, that's all. Great. So you can take a common n by 2, which is this one is 1 log twice pi plus rest is as it is minus half v plus log beta 1 half log, this is log. Similarly, log likelihood function for restricted estimator is again first bringing in all elements. Well, ut is beta naught yt plus axt. We already know that. V inverse is y by t 1 by t ut transpose, we also know that. So basically this becomes n again. I mean this last element becomes n by 2 again. Basically they give you the same shape. There is no change in the shapes between the restricted and unrestricted for a multiple equation model. Great. So now the likelihood ratio test is minus 2t log LT theta naught theta 1. They have given you the same shape. There's no change. So basically t, previously we had for one case log v naught minus v1 minus 2t log v naught minus v1 log v1. In the special case of SUR, seemingly unrelated regression models, b is identity matrix, then we are only left with the first element in case of a seemingly unrelated regression models when b is IN, because we don't have beta, we don't have dependent variables to be in the function of dependent variables. So let's look at an example. Sorry, testing a multiple equation model. We have y1t beta 1 y2t plus alpha 1 x1t plus u1t y2t beta 2 y1t plus alpha 2 x2t plus u2t. Simultaneous is just a simple structural equation model or simultaneous equation model where residual is 0, mean and variance, sigma variance. Again, restrictions, null and alternative are to put restrictions on alpha. Let's first simulate the data. First stage in the first local function is to simulate the data or use the given data. The restricted parameter estimates are obtained by imposing the restrictions alpha 2 equals minus alpha 1 and writing the model. Well, pen and paper with the restrictions. Now we have a negative sign because alpha 2 minus alpha 1, alpha 2 minus alpha 1. So instead of writing alpha 2 again, we just put minus alpha 1. x1 is 2. And now the likelihood ratio test is restricted minus unrestricted chi-square distribution. Present value, probability value is estimated 0 0. Restriction which is probability value is 0. That means the restriction is rejected, null. For we can reject the null hypothesis of the restriction at 5%. Alternative form of the statistics is, well, log v naught minus v1, that we are already familiar with, log beta naught minus beta 1. In case of seemingly unrelated regression, the second element becomes 0. Notably, a equals b. So world statistics on the other hand is 0 1 0 1. How are we getting 0 1 0 1? Where are we getting 1? Very simple. 0 1 0 1, that's all. Q is 0. Q is 0 because Q is generally 0 in most cases in the restrictions. So compute negative Hessian. Worst statistics is T at 31 minus Q at or Hessian. Well, we know the world statistics equation. This is the world statistics equation. For LM, first compute gradient and then compute OPG and the Jacobian. Yeah. So now we can move on. We have gone through seemingly unrelated regressions, and before that FIML, which is summation of y1 x1 divided by summation of y2 x1, and then we have to compare that with instrumental variable estimator. That's quite big. Let me see if I can remember. Y1 inverse x, y1 transpose x, x1 transpose x inverse, then x1 transpose x transpose, sorry, y1 transpose x, x1 transpose x inverse, then x transpose y1, multiplied to y1 transpose y2 transpose x, x2 transpose x inverse, then x2 transpose y1 instead of y2. That was the instrumental variable. But then again, let me just check the instrumental variable, which is inverse of omega transpose x, inverse x transpose x, then x transpose omega, or omega into omega transpose x, inverse of x transpose x, then x transpose y. Just that's it. So this is the instrumental variable. Now we will look into problem 4, problem 5, and I think problem 6. I'm not sure if we can also look into more problems from here. Okay, oh yeah, we can also have a look into problem 7, which is pretty good. Okay, well, now we intend to solve 4 problems from number 4 to number 8. The first problem is weak instruments problem. This exercise extends the results on weak instrument in example 5.11, which means if we are to go back to the notes, this example is extending on weak instruments. So here we have weak instrument equation between y to t, u1t, y to t is alpha, xt, u to t. Weak instrument is when the distribution of the instrumental variable is not asymptotically normal. So, or in another way to explain it is when your alpha is less than the value of alpha is less than sigma, it's a weak instrument problem. Okay, so there is our instrumental problem. Consider the model y1t beta y2t u1t plus y2t alpha xt plus u2t. We have already seen that, in which y1t and y2t are dependent variables. X is IID, which is uniformly distributed. 0 mean 1 standard deviation is the exogenous variable, which is fixed in repeated samples, and the parameters are beta and alpha. The sample size is t equals 5, and there are 100,000 replications are used to generate the distribution of the estimator. Number A, generate the sampling distribution of instrumental variable estimator for the parameter values beta equals 0 and alpha equals 0.5, 1 and 10 given. Discuss the sampling properties. Are they asymptotically normal or not, right? If they're asymptotically normal, then it's fine. If their distribution is not asymptotically normal, that's a weak instrument problem. Generate the distribution of instrumental variable estimator for the parameter values of beta equals 0, alpha equals 0. So beta 0, alpha is 0.5, 1, 10, beta 0, alpha 0. Compare the sampling distribution to the 3 sampling distributions obtained in part A. So for 3 alpha values, we have to do distributions. Alpha against, we have to compare that with alpha 0. Also compute sampling distribution of the OLS estimator for this case. Note, for this model, the OLS estimator has the stock, right, and Yogo property. which prelim OLS is sigma 1 2 by sigma 2 is 0.19. Repeat parts A and B for sample of size t equals 50 and 500. Discuss whether the results in parts A and B are affected by asymptotic arguments. T5, then we have to do T50 and T500. Alright. So program to generate figure 1A of stock, right, and yoga weak instrument paper. Great. First thing is to clear the screen, as we already know, blah blah. In R we do remove object, which is all equals true is all true, then least equals is. Least means all xy, for all xy and everything is all true. RM graphics off. Then state 1 2 3 4 random number generated with Marson and Twister state, and random number into the state. Just simply this could have been done with random stream set global stream instead of doing all this trouble, you know. Asset seed 1 2 3 4 kind Marson and Twister. Helper function for inverse and for figures. We need to load this helper function in R. Load KS library. We'll need KS library for this. So we need to do 100,000 replications. First, the sample size is 5, beta 0, 5.25 given to us. These are all given to us. Let us check whether the phi value is given to us. Okay, phi equals 0.25. Here also we are creating the function, putting everything in function here in R. So linear weak is the function that is being created, and we are doing the code between the third brackets. T5 beta 5.25 sigma 1 sigma 2 sigma 1 2 sigma 1 sigma 2 is 1 and 1. Sigma 1 and 0.99, right? So these are already given to us. Omega is sigma 1, this is the variance covariance matrix. Sigma 1 sigma 1 2 sigma 1 2 sigma 2 2. Omega is first create a matrix, then column bind sigma 1 sigma 1 2 sigma 2 1 sigma 1 2 and sigma 2 2. Then by n number of rows is 2, by row is t. Then the row is sigma 1 2. We already know this equation too. Let me still show you that. Here, sigma 1 2 divided by root over sigma 1 sigma 2 2. So row sigma 1 2 divided by square root of sigma 1 multiplied to sigma 2 2. Row is simply, we don't need a matrix here, sigma 1 2 divided by square root of sigma 1 1 multiplied to sigma 2 2. X is random number generated. We're doing Monte Carlo replications now for t observations in one column. Column bind run if. So here is column bind, not row bind. We're doing it by column bind run if t up to t. Or we could have done x divided by x transposes. So beta of IV estimator, we're gonna estimate beta of ID estimator with simulation now. First create zeros to store the results after n rows and one column. Replicate zeros n times. This is not important, this is just text progress bar. We want to see how things are progressing. It's easy to do in R, so a lot of people would like to see because it's a simulation and with 100,000 replications. So for I equals 1 to n, this is moving random. We don't need to do it. U equals random number of t and length of omega, t rows, and length of omega means total number of parameters represented up to total number of parameters. For every equation we need a residual, right? So random number generated with that multiplied to the Cholesky decomposition of omega, the diagonal matrix multiplied to the Cholesky decomposition, just like before. For I in sequence n, the bracket begins again. U is equal to matrix, first matrix, then C matrix, and R norm. So not C, sorry, R norm is random number. So RNDN is R norm, and simple RND is RANIF. Random R norm, random number multiplied to number of rows of omega. R norm is T multiplied to T and number of rows of omega. Columns will be automatically set here, or it must be given to us. I'm not sure. It's pretty difficult here in R. T multiplied to number of rows of omega. Okay, that was not necessary here. Did we mention it anywhere? No. T is fine itself. T is 5. Sure, number of columns is 2. You have to be very specific here. You cannot let it auto generate. So T is number of multiplied to number of rows of omega. So it will be same as length of omega multiplied, and number of columns is 2. MATLAB is much easier in this case. This is a matrix that is multiplied with Cholesky of omega. So first 5 number of T number of rows of omega means T will grow according to, you'll have T according to the omega's rows, how many rows are there in omega, and you need basically it could have been column 2, not a big deal, because omega itself is a square matrix. Number of columns is 2 because you have 2 parameters, you want 2 columns. So W, which is necessary, this is y1. Instead of W you can mention y1. So what was the equation? See, equation x, right? So y2, sorry, W is y2, x phi u1, right? X phi u1. Okay. X phi u, all rows first column. W beta, beta comes in the first equation, y equals, now because y2 goes into y1, right? Y1 doesn't go into y2, y2 goes into y1, so W goes into y. So x phi u, all generate all the u you have generated, you take first columns. W beta, all the u generated for second column. So same thing, W beta, it will automatically take all rows. And then let's prepare for the loop for what? For the instrumental variable, inverse of x transpose x, which will come in between, right? TMP, inverse of Tx multiplied to x, then TMP1, x multiplied to inverse of x transpose x multiplied to x transpose, good, x multiplied to TMP multiplied to transpose of x, then W transpose multiplied to TMP1, just like Lego, setting a block like Lego. W transpose multiplied to TMP1 transpose, then finally inverse of TMP2 multiplied to W. Now you have everything, W transpose multiplied to inverse. So what was the equation? Let us have a look into the equation. So many things we have actually covered, seemingly unrelated. No, just before that. Recursive, no. Here, inverse of W transpose, inverse of this thing. So inverse of TMP2 is W transpose into TMP1 into X transpose inverse of, so whole thing, easy, multiplied to TMP2 again, whole thing, multiplied to Y. So TMP2 is the whole thing multiplied to Y, inverse of W transpose into TMP2. That's all. That is your IV estimate, easily done. Let me see how this is done in R. Yeah, same thing. So the text progress bar ends here, close. These two commands are for text progress bar. And then we do a graph, which we can do manually, I believe. So sequence is 2.001. We want xi to have -2 to 2, then ks density, if its ks density is a function, so we want to see the density. The problem was asking us to do a graph, that's all. So yeah, we wanted to see density of instrumental variable for xi. Okay, same thing done here. And then we are supposed to, this is a default command, there's no specific here. Generally switch of text interpreter, latex interpreter, and clear figure. So just clearing the figure. So plotting xi and f. Xi is a range and we are plotting the density. K's density or the density function is being plotted, that's all, nothing else. Here is also the same, K's density plotting, and just black in black, label and box, these you can do yourself. Just this is the tweak here we need to remember. KDE, here K's density, in short in R is KE. First X, then Y, H is 0.07, evaluation points is xi. So this is by this equation, what this equation demands, what this function demands. Okay, so H 0.07 evaluation points xi. You can have a look into that anytime you want in the help, like here you can type KDE. Let's see what comes up. Okay, KDE, Let's see if R could found something. You can always Google. R has a very big library. The non-central distribution. Let's do it again. Compute a bind smooth kernel representation, basically smooth kernel representation, yeah, something like that. All right, okay, we don't want that for now, because we need to deal with this. So okay, this problem is solved. Now we need to, we're just gonna close it, and we did 100,000 with 100,000 replications. We estimated in a loop, we estimated the instrumental variable, and in a loop with 100,000, or when we estimated instrumental variable, you can see we can simply plot it, you know, against anything we want. That's all. That's the point of this exercise. And then the second problem that we have here is regression model with gamma distribution. So we'll use the linear gamma code. Consider the linear regression model, value by t beta naught xt plus ut minus rho alpha, in which yt is independent variable, xt is exogenous variable, and the disturbance term ut is an IID drawing from the gamma distribution. Good. This is IID drawing from gamma distribution. 1 by rho p. We don't need to remember because the functions are there in both MATLAB and R, with tau rho representing the gamma function. The term minus rho alpha in the regression model is included to ensure that the disturbance term ut minus rho alpha has a mean 0 for sample of size t, different size. We are talking about 10, 100, 1000 and 100,000. Compute the standardized sampling distribution of the least square estimators. Nowadays it's very easy. You have the function of z norm or z self. You can simply call it with a function and it will do the standardized distribution for yours, for any distribution automatically based on 5000 draws. So you need to do 5000 replications. Parameter values are given: beta naught, beta 1, rho, alpha. Xt is drawn from a standard normal distribution. Discuss the limiting property of sampling distribution as t changes. Limiting property, p-lim, of sampling distribution as t changes. So we want to talk about the limiting property here. First thing first, we need to remember that in MATLAB the gamma random distribution function is gamma random, where a is shape, b is a scale, generates gamma random numbers. Right? Okay. All right. Linear gamma. First, the problem is giving us some values already. We have a gamma random distribution, and we have t, which is 10, 100, 100,000, up to 100,000. We need 5,000 iterations. Beta naught, rho, alpha, all these values are given to us. Let's see. Is there any local function? No, there is no local function. So okay, we'll just go with this. First of all, number of draws is 5000, that is given to us. Before that, clear all CLC. Just memorize all true, is all true, least equals is all goes to RM. Parameters given to us: beta naught 1, 2. Beta naught 1, 2 means beta 1 and beta 2. Beta naught 1, 2, I'm just creating a vector to make things much easier. So here C or combine 1 and 2. Row point. Do you recall that in MATLAB you have third brackets in R? Most of the things are done in first bracket. Third bracket is only in a loop, and the functions go into the second bracket. Always remember that, very easy to remember. Row is given to us, alpha is given to us. So random stream, set global stream, random stream, MT19937 AR seed 1, where set seed we can do 1 or 1 2 3 4 5, anything, kind, master and twisted. First, starting with T 10 X, always remember the first row is ones, first column is ones, second is the randomly generated columns. I don't know if there is specified what is the distribution type. No, standard normal distribution, not uniform distribution. So I think this is RNIF. Yeah, no, R norm, very confusing. So RNIF is uniform distribution. So column bind, replicate 1 t times, replicate 1 t times, then R norm t, it will automatically do it. Z1 and Z2, we need to calculate 2 Z1 and Z2, zeros, end rows 1, zeros, number of replications by end rows 5000, zeros, end rows 1. We'll see why 2 Z's are required. Oh yeah, we need to estimate the two standardized sampling distributions that we want. So this is storing. Replicate 0 end rows, replicate 0 end rows. Again, this is not necessary. For 1 to number of rows 5000 times, u is equal to alpha. Okay, u is equal to what? Alpha, row alpha, u equals, no, you just break it and take u here on the left hand side to put everything on your right hand side. So it's equal to alpha. Then a random distribution of row is required, alpha multiplied to gamma random. So row, shape and scale, right? Row is the shape, gamma random first comes, row is the shape, and 1 is the scale. T rows first column, up to T rows first column. Shape, scale, 1 is scale, row is shape. Okay, so alpha into gamma random distribution of that, minus row into alpha, right? Minus row, ut equals yeah, yt minus beta naught minus beta xt equals row alpha. Oh, then simple row alpha. So alpha into gamma, ut equals minus expected value ut minus row alpha equals 0. So ut equals first alpha into row, isn't it? First alpha into gamma random distribution, yeah, rows gamma random, minus row into alpha without the distribution with the given value. Gamma function, the term minus alpha in the regression is included into the disturbance term. ut minus has mean this. All right, okay, this is the trick. So one with the distribution, gamma random distribution, with the row, and another one is with given row. Okay, so this is the difference. Let's see, alpha into r gamma. R gamma is the function for gamma random. N, see, r gamma n, shape, rate, scale 1/8, n, As you can see, number of observations t, which is given in MATLAB t rows, one column. So t rows, shape is row, scale is 1, and rate is 1, scale is 1 by rate, which is 1 by 1 equals 1. So scale is 1. Same first, in MATLAB we start with first shape, then scale, then m rows n columns. Here we start with not necessary to put how many rows you have, how many columns you have, t rows, shape, scale, that's all, minus row alpha. Very simple. Then y equals, with this information we estimate y, beta naught x plus u. Beta naught x plus u means beta naught transpose, basically beta naught transpose, because to give it a column shape, nothing else. Beta naught x means both beta 1 and beta 2 comes in here, plus u. Here x multiplied to column bind beta naught, column bind beta naught, because beta naught has two values, so you want that to be in column, the whole thing you want to be in column. So x into column bind beta naught plus u. B equals regression, x by y. B equals regression, here b equals lm, linear model, y x, y x on y, that means that minus 1. I'm not sure why minus 1, but always it is like that. And we just, beta will have only the coefficients from this linear model, only the coefficients. Okay, then e equals y minus bx equals y minus bx. B and x now both are matrices, because b is a matrix, as we know, x is a matrix too, and sigma is E transpose E divided by T, sigma T transpose ET. Fine. Variance covariance matrix is S2 multiplied to inverse of X transpose X. X2 multiplied to inverse of X transpose X is coming from, because it's a structural equation model, sigma square divided by x square, x minus x bar whole square. We are already familiar with that. So z1 is b1 minus b0. Let me see, b0 for b0 minus b0 by standard error. So b1 minus b0 1, b2 minus b0 2. Okay, let me see, b0 minus, okay, b0 1, b2 minus b0 2. b0 1 is the first element of b0, b0, and b1 is the second element. So, and b1 and b2 is coming from the loop when we are doing the first element and the second element, when you are doing this regression, divided by square root of first row, first column, second row, second. Okay, so diagonal element, square root of the variance covariance, the first diagonal element of the variance covariance matrix, the second diagonal element of the variance covariance matrix, which is the standard error actually, not square root of VC, is same thing. Okay, so progress bar ends here. For t is equal to 100, do everything again, nothing changes, plot the results, and simply just plot it with subplot. Z1 against set limit minus 5.25 up until 4.75. Well, fine, histogram, you want a histogram, no big deal, no biggie. bar mfro c22 b. This is something you need to either copy from given codes, remember it, or just there's no point of understanding it, because in most cases you should be able to create plot from plots, you know, or here also plots function is given. So this is gamma distribution in a loop. What we did, the trick, the most important thing was u, whether the gamma distribution minus the alpha, so you wanted u and then you wanted to find z1 and z2. Now you are plotting z1, z2, z3, z4. So z's, you are plotting z for each unknown parameter. Z, let's not just think about this. Z for each unknown parameter, 1z for each of the or specifically 1z, yeah, 1z for each of the equation, I guess. How many equations were there? Oh no, just one equation. Yeah, each of the unknown parameters, beta naught and beta 1, and you are checking the distribution. That's all. So that was gamma. Now next problem is 6. Okay, number 6 is to find relationship between full information maximum likelihood and instrumental variable estimator. So simulate the following structural model for 500 observations. This is a structural model, and as we can remember, in structural equation model, dependent variable can be a function of dependent variable can be a function of dependent variable and exogenous variable. Okay, always remember. So here we don't have another exogenous variable, we just have one exogenous variable in which y1t, y2t are dependent variable. X is IID with 0 mean and 100 is the standard deviation. Given 100 is the exogenous variable. U1t, U2t are IID normally distributed. Disturbance terms is 0 mean and diagonal covariance matrix. This is diagonal because the non-diagonal elements is 0. Diagonal covariance matrix, and the parameters are set at y because there is just one x. If you have more than one x, structurally the non-diagonal elements would not have been 0, and the parameters are set at beta 1.6, beta 2.4, alpha equals minus 0.5. These are given to us. Compute full information maximum likelihood estimates of the model's parameters using an iterative algorithm, maybe Newton-Raphson, with the starting estimates taken as draws from a uniform distribution 0 and 1. Recompute the FIML estimates using the analytical expressions given in example. Compare these estimates with the estimated obtained part in A. Re-estimate the model's parameters using an IV estimator, and compare these estimates with the FIML estimates in part A and B. So 5.8, page 36. Okay, analytical expressions given for full information maximum likelihood. So this is analytical expression given in 5.8. So here we have x1t and x2t. In the new case, in the example, I have just one exogenous variable. So we need to compare our results with this result. Okay, fine. Let us have a look. So is there any local function to begin with? Yes, there are. Great. The first local function is to simulate the data given the information to us. Given the information to, we need to simulate our data. Construct alpha a, b, and u, and we need to simulate the model by simulating the reduced form. Then we need to do log likelihood function, and then we need to do concentrated log likelihood function, then quite a few functions. Okay, let's start looking into this. First, let's simulate data. Random stream, set global stream, function, well, this is into function t, beta 1, alpha 1, beta 2, alpha 2. All these will be given to well, resulted to us. Alpha 3, beta 2, alpha 2, beta 3, alpha 3. Fine. Beta 0.6, gamma 0.4, alpha minus 0.5, omega 2, 0, 0, 1. Generate simulated data by simulating the reduced form. This is what is coming from here. Okay, so in MATLAB it was quite easy. We started with the two equation given information in R. We're taking a different approach, I guess, because we're looking into number 2. So omega is 3 by 3 here, not 2 by 2, because the first 2 by 2 is as it is, but then it okay. Five. The question is where is 5 coming from? Compute model 0 t is equal to 500 observations. I'm truly not sure where 5 is coming from, but okay, let's proceed with this. Construct population parameter matrices 1 minus gamma minus beta 1. Well, that is, we already know 1 is gamma, 1 is beta, and in B we have minus b1 minus b2. It's just that 1 minus beta 1 minus beta 2, 0 1 minus beta 3 is easier. Good, because now we are talking about 3, because here in R the code is built around this equation where maximum number of unknowns are there. So beta 1, alpha 1, beta 2, alpha 2, we want you to have everything, given that the structure is this: beta 2, beta minus beta 1 minus beta 2 minus beta 3, 3 rows by row t. A is 0 minus alpha. C matrix is combining minus alpha 1 minus alpha 2 minus alpha 3, 0 0 0 0 0 0. Okay, fine. Number of rows, fine. Construct exogenous variables 10 is given there in the question. 100 squared, 10 square root of 100 is 10. Random number of t, rows 1 column. Column bind first variable t rows 1 column. Exogenous variables, here we are talking about how many exogenous variables? 3. Why 3? x1, x2, which one is the other one? W? Probably, yeah. They're also thinking about W here. So okay, fine. Okay, what am I looking at? Oh bloody hell, I'm extremely sorry. This is different problem in R. I'm sorry folks, that was very funny. I was looking into some other course from R with the IV codes from MATLAB. That's why these codes were a bit different, you see. So I'm gonna go through R code one more time. I was looking into the recursive model, another problem, so just forget about it. Yeah, exactly the same number of rows, 2 rows, and up to these nothing changes. Column bind 10 is given to us. And yeah, let's move on to our local function. So after this we were there, then construct exogenous variables. So matrix r norm t r norm number of random variables, t rows, 2 columns, 2 residuals multiplied to Koleski. So to r norm t2 n col number of columns multiplied to Koleski decomposition. Inverse b is simply inverse of b. Then simulate the model from the reduce from equation. So we're gonna simulate values for y. Y is zeros, t2, well, y is array 0 of 2 columns. For I equals 1 to t, I in sequence t, y, x, a inverse b plus u inverse, well, this is what, y equals minus a by b, x minus x by b plus u by b. Okay, that is the equation that we had from reduced form. So this is the same thing, x minus x a b, same thing. And then this function returns x and y, list x's, y, y. So this function returns x and y. Yeah. Okay. Then preparing for the next one, negative log likelihood function theta y x mean. So return lf. This function return a neg log function. The neg log function, then the outputs, then the equation lf minus mean log lt theta y x. Return lf log likelihood at each observation. The function is log lt, is the function with theta y x is the input, t, and t is n row, and n is n col number of column, b 1 minus theta 1 2 minus theta 1 1. So with a matrix c, a matrix, then combine 1 minus theta 2 minus theta 1 1. The number of rows 2 by row is t. A is 0 minus theta 3, fine. Matrix A is matrix and combine 0 minus theta 3 in row 1, b row 2. U is zeros, E residual is zeros, T rows and columns, right? Because for everyone there will be residual. It is 0, CTN. So construct residual for this is the residual equation, by plus ax, x plus by. Very simple. Equals by plus ax, by ax. The loop ends, begins and ends. Concentrate out residual variance covariance matrix and restrict it to be diagonal. Now we have to do more work from the derived residual. Okay, so here we derived with simulation with loops, we derived residual, and then we need to concentrate out variance covariance matrix and restrict the variance covariance matrix to be diagonal only. So I mean to I is minus 1, omega is identity matrix and identity matrix. What is the use of these? I'm not sure. We'll see. Column col means col mean. Oh, this is just column mean. X false dimension 1. This is the mean of the column. U square, here E square. Omega diagonal 1 up to n, diagonal up to n, which is diagonal of me2 mean column. And then the log likelihood function. We're familiar with this already. Return the log likelihood function. Fine. Okay. What am I doing here? Hurn j in column omega. That's another for loop here, right? Oh, this is a j up to omega. So omega is being created, this one, because there is no identity matrix basically. So this portion and this portion comes together because we don't have any identity matrix in R, so we need to manually create the identity matrix. So sequence up to omega, heteros j column coming from me2 me2, which is the column means of U square. I is -1 up until I something. This is the sequence to create the identity matrix. Pretty long step. Okay, fine. Then instrumental variable estimation, instrumental variable equation. We are already familiar with this. Starts from w prime x inverse of and then ends in y. And because it's quite big here, so we need to like break it down. We want to break it down for R. MATLAB is in a lot of sense, as you can see, much easier. So the function here ends here. Instrumental variable, standard errors of regression, FML and IV estimation. So standard error of regression, this is not given in R. Alright, fine. Standard error k is size w2t size 1 sigma square root. Just to remember, we need to define error, we need to define the size k, we need to define t because it's a rectangular matrix, we need to define sigma for variance covariance matrix, we need to define sigma square multiplied to inverse of this is also given in our notes, if we can remember. Square root of diagonal variance covariance. So fine. Instrumental variable estimation. Okay, sigma square. Let me go back into our notes to show you where this sigma square is coming from. Just need to go to the discussion that was talking about instrumental variables. Bear with me a minute. No, this is today's topic. So this is where it all began. Simultaneous This is the equation relevant to the instrumental variable, where this was the instrumental variable equation, and this is sigma square divided by the, in the numerator you have the, I think this is a mistake, it must be, no, this is correct, because we can simply multiply with the inverse. So here we have multiplied with the inverse to find the instrumental variance covariance matrix of the instrumental variable. That's fine. Now let's look into the equation itself. So there is one tweak up until now, which is in R we don't have the identity matrix, so we need to first put -1 in I, then we are doing J is 1 to the size of omega, where I rows and J columns. In I rows and J columns will be stored the mean of the columns up until I, where I equals this will happen up until I, so I equals 1, all values in I equals 1, and this will continue up to J columns, 1 row and J columns for this, and we will continue to increase I by 1 I will have I plus 1, and that will happen up until the total number of omega is reached from 1 to n. Alright, this is pretty complicated. Okay, now let's look into the estimation itself. So first, as we know, first we have to do 500 observations, or let me have a look into the problem. 500 observations are there, so t is equal to 5. Then we need to call the simulate data function. Here theta naught is being created randomly with run if, because it's a uniform random distribution. Because it's a uniform random distribution in theta naught, run if is okay. So model using an iterative with the starting estimates taken as draws. So theta naught is the starting estimate for the optimization problem. It's taken as draws from uniform distribution. So sim results will call the simulate data function that we have created before, where in X the X column information will come in Y the Y column information will come in U the U column information will come in from simulate data. Then we are to optimize. So theta is equal to theta neg log theta y x random 3 1. We have already done the concentrated log likelihood function, which we have included in theta neg log function. So on the other hand, optim theta naught, here we didn't generate theta naught, it has already been generated. Theta naught is the beginning one. Oh, here random 3 rows 1 column, this is the beginning, this is the initialization, and theta naught run if 3 is the initialization. Neglog YYXS method has Newton-Raphson algorithm. With Newton-Raphson algorithm, in theta we'll just get the power, fine. Then concatenate and display starts with n, ends with n. First is beta, then gamma, then alpha. Values are shown in theta separately. Then construct residuals and estimate covariance matrix, right? So T is equal to n row, n is equal to n column, B is matrix, then combine 1 minus theta 2 minus theta 1 1, number of rows 2 by row T. A is again matrix, combine 0 minus theta 3. So again things are being repeated here, and residual we have to do again, construct the residual in loop. Zeros Tn y array, we're gonna store in array 0 Ctn 1 to T. So the reduced form is by plus ax. mean, then diagonal variance, the diagonal elements omega. We did that. Then concentrate out residual variance covariance matrix and restrict it to be diagonal. Again, we have to, because the diagonal function is not there in R. MATLAB is much easier in this sense. It has the functions necessary. So first find the mean. Okay, fine. Then the diagonal elements you can separate out. Now in I you put 1. Then for j, which goes from 1 to the size of omega, or here the length of me2. So you make use of drv, where the diagonal elements are being stored. ij, you'll put in, if they're 0, they're zeros. If they're not zeros, you'll put the mean, column means squared from I, and that will go on up until I equals I plus 1. Fine. Now full information maximum likelihood analytical solution. Okay, remember sum of y1x divided by some y2x, that was the FIML estimation. So let's see if we can find FIML from the notes. FIML full information. Okay, so there we have the full information maximum likelihood estimator, where we have beta as given, E1, or say, yeah, error is y1t minus beta 1 y2t. This is the estimated parameter beta. Okay, the estimated parameter y2. I'm not sure what num is. Some y2, some x2 minus some x1 y2x. Numeric of something. Let me see what num is. Okay, I'm not sure. This is the density y2. Okay, num is some y square e1. Okay, so sigma hat is here being put as num, where some y2 x square, yeah, y2 e1 minus x e1 sum of y2 x. So this one, x square and x square and x1 remains same. Num by den, gamma finally is num by den. So x square and some xe1 remains same. Y square multiplied to e1, y2 e1 y2x, y1 e1 y1x. So y1 e1 y1x, y2 e1 y2x, y1x, y2 e1 y2x. Something like that. And gamma and alpha, gamma finally is num by den, and alpha y1 e1 y2x minus y1x y2 u1, y1 u1 multiplied to y2x, y1 y2 u1 multiplied to y1x, u1 multiplied to y2x, y2 u1 y1 u2 multiplied to x. This is num by den alpha. Okay, something very tricky. FIML analytical solution. So we in theoretically we have already only introduced these. Okay, now how do you converge them is a question, and the convergence happens like this. So whenever you're doing gamma, y2 u1 into x square minus x1 x1 x u1 y2x y2 u1. So y2 u1 y2x, you have x square and x u1. Then y1 u1 y1x, we have x u1 and x square, same thing. What changes in case of alpha? y1 u1 then y1x. Okay, but with that multiplied is y2x and y1x. y2x and y1x is multiplied with that. Now y1 u1 y2 u1 y1x y2x y1x, that's all. It's a completely different thing in the numeric numerator and denominator. Okay, here is also the same. Instrumental variable estimation, beta 1 IV, you just call the instrumental variable from the function. It will automatically give you, when you call IV, it will automatically give you y1 y2x y1 u1 and beta 2 IV. See IV ywx, it will give you everything. We want the results to be as matrix. As matrix TMP y2 is combined y1 matrix C E1 TMP E1 is C E1x and column. The representations in R is sometimes bullshit. TMP y2 TMP y1 TMP E1. So beta 2 is y2 y1 and E1, and beta 1 is y1 y2 x. First equation, second equation, beta 1 and beta 2. Estimator solving the equations. So there we have the linear equations. Instrumental variable problem is completed. Then the next problem is recursive structural model. Simulate the trivariate structural model for t equals 200 observations. Okay, it's a structural model, so you have a structural lower triangular representation in which the exogenous variables are x1, x2, x3 are IID and mutually independent random normal variables with zero means and standard deviations of 1 to 3. The parameter is a 0.6 given to us. The disturbance vector u1t, u2t, u3t is normally distributed to zero mean and diagonal covariance matrix. Estimate model by maximum likelihood and compare parameter estimates to the population parameter values. Estimate the equations by OLS and compare with maximum likelihood. Briefly discuss why the two sets of A and B are the same. So this is your linear recursive. Linear recursive. Is there any local function? Yes. First, simulate data. Given the information, construct. First, we need to construct beta and alpha, B and A, beta 2, beta 1, beta 2. So, fine. 0 1 minus beta 3 0 0 1. Beautiful. These are given to us mostly with all the given information. We just put them, construct exogenous variables. Exogenous variables are not given to us, so we will just randomly generate them. Random number t1 cbind 1 random number t, 2 into random number t1, 3 into random number t1, just creating 3 different random variables. That's it. Construct disturbances. Disturbances is very easy. Random number t3, use matrix R norm t3, number of columns will be 3, multiplied to Koleski decomposition of the given omega. To construct disturbance, we need the omega. Simulate the model by simulating the reduced form, and by simulating the model we'll get y's. So for y we'll create array 0 and combining t3, or here for I in sequence of t, begin the third bracket, y I equals minus x I a inverse plus u by b, ax minus x by b plus u by b. The loop ends, then return is list x, y, u, omega. So the whole thing with the whole loop, we get x and we get y, we get u in this function. The function when is completed gives us x, y, u, omega. Then comes log likelihood function, just like before, nothing here. Rows on just in log likelihood function instead of the values. In simulate data we put all the values that we know, and we simulate u's from there. Given the beta values, we simulate u's. Using u's or the disturbances, we simulate disturbances from the omegas, and using the disturbances and other given values we simulate y's. But for log likelihood we don't basically include any given information. We just give it a structure, actually mentioning where the thetas should locate. That's all. Construct residual and concentrate diagonal covariance matrix, zeros for I diagonal TMP. First construct the residual. We have constructed the residual BA, then constructed the residual, fine. Then omega TU UT, omega is diagonal u is equal to 0 CT. Okay. Residual, concentrate out residual variance covariance matrix omega from here. Concentrate out residual covariance variance covariance matrix, diagonal of TMP, TU multiplied TU by T. Oh, this is just this. That's all. This one is just diagonal, without diagonal. This is just this. Done. This two is not being done, so we are skipping that. Okay, let's see what happens. Zeros, fine. Then the sequence is created with the equation. Is the same in the equation, except for whenever we're talking about matrix they'll come in. And finally the transpose I rows will be represented in column to make sure to reassert cbind ui. That's all, nothing else is the tweak. So return log n. So we are not basically simply concentrating out residual variance covariance matrix and not giving it a format. Here in MATLAB it was able to give it a format. Then we do the analysis. Results table. Okay, this is a results table. Have a look. This is a results table. Row names, column names, results, number of rows equals the length of our names, column names. First fix the length of the dimension, then give the names of the dimension. Now the recursive function, information is given to us mostly, we'll include them again. Then we will call yx to be simulated, because we have already, remember in simulated what did we do? We used the given information from x. We estimated the residual or simulated the residual with given omega. Then we simulated in loop the y's with given x and given estimated disturbances. Now here we're just calling it so that every information is stored, where we single out x, y, u, omega, and then we initiate, because there are 6 parameters, so there will be 6 estimate parameters by values, and then we simply do maximum likelihood estimation. Fine, theta. Comparison is create empty table, I'm not sure. Actual is comparison 1, ML estimate is comparison 2, C theta. Oh, we are making a comparison table for presentation. OLS estimation is x and y. Equation 2 is y1 x1 divided by with y2 y1 to x1 y3. Equation 3. Okay, beautiful. y1 x1 y2, see, sorry, y1 x1 y1, then y1 x y1 x1 y2, y1 x1 y3. That's the spirit. Y x1 y2 y1 and x1 y3. On the other hand, linear model y1 regressed on x1, y2 regressed on y1 plus x1, much easier. y3 regressed on y1 plus y2 plus x1. Comparison OLS is equal. It's comparing true and estimated parameter values. Actual MLE OLS theta theta OLS, equation 1, equation 2, so combined, the values are combined. Okay, compute covariance matrix U0s T3. Okay, so compute covariance matrix. First we need to compute the residual. Again we have to define beta A, and from there we need to compute residual. Then we take omega, we estimate omega, which is the diagonal of the residual, and we have omega, which we compare. Omega TUT. See, we don't need the identity matrix at all here in R, which is just this transpose in comparison diagonal omega hat. This is just the comparison. Quite simple recursive model. There's just one last we will do today, linear SUR, assuming unrelated. Taylor and other applications will probably not deal with. Seemingly unrelated regression. Simulate the following trivariate SUR model. Linear Taylor series. Taylor was another slow. Klein's macroeconomic model of United States. These we can have a look, but not right now. Okay. Now let us talk about seemingly unrelated regression. As we remember, seemingly unrelated regression is when the models have dependent variables to be functions of exogenous variables only, not another dependent variable. So we need to simulate the following trivariate. Again, remember, when we are talking about simulation, in the functions we take the given values, we simulate the disturbances from the omega given value. Using that disturbance, we simulate dependent variables. That is simulation. Simulate the following trivariate SUR model for t is equal to 500 observations, in which the exogenous variables are IID and mutually independent random normal variables with zero mean and respective standard deviations of 1, 2, and 3. Parameters are given again. Disturbance vector, the covariance matrix of the omega is also given to you. Estimate model with maximum likelihood estimation when compared with population parameter value. Estimate with OLS, compare it with MLE. Simulate model using changing the omega. And first we are doing it is equal to 500 observations. Simulate the model using the initial covariance, repeat percent win, comment on the results, just doing the same thing again and again and again. So linear seemingly unrelated regression model. Let's see if there is a local function. Indeed there is local function. What are the local functions? To begin with, the log likelihood function. Okay, the log likelihood function, number of rows, number of columns. We don't need the identity matrix because R cannot create identity matrix. So R cannot create identity matrix. Simply diagonal values of n are taken in B. Okay, fine. A is matrix, combine these into n columns and t rows. N is number of columns of y, or you could have simply put 3 just to make it a bit more tricky. Zeros then coming in where we are estimating the residual 1 to t by plus ax. Fine, concentrate out residual variance covariance matrix. From the residual we concentrate out omega u transpose divided by 3 t. Then we estimate log likelihood function using the omega. Log likelihood function requires log pi. B is already estimated, determinant of B and determinant of omega, remember we need that. Everything remains same. The only trick in R here is, you see, in the decomposition u transpose inverse of omega, right? The transpose is shaped with column bind ui, so this is row binded automatically. We want this to be in column bind. That is the only trick with the decomposition, nothing else. Log likelihood, before that there must be simulation local function. I see in MATLAB it's not there, so again simulation with omega. B is diagonal of diagonally you put ones, number of rows will be of omega. Okay, diagonally you put ones of the number of rows will be from omega. Diagonally put ones is b. A is again calculated separately, omega. Okay, diagonally. So let's see what does that mean. Diagonal x equals 1 and x equals 1, number of rows and number of columns. Number of columns is not necessarily number of rows, where omega is fine. X equals 1. This is by default always. So diagonal of omega, that's all. Very simple. Exogenous variable being created randomly, disturbances being constructed, as well as exogenous variable with Kolesky decomposition. Then using the disturbance and the exogenous variable, we are simulating result for y, and then we are simply asking the function to return this. Okay, now let's have a look into the main model. Random stream, set global stream, b identity matrix 3. That's what we did here in the previous function. Okay, diagonal of 1. So x equals 1, number of rows is omega. It automatically created. Exogenous variable being created. So in MATLAB code we did in the main body, we created a different function for r. So here exogenous variable disturbances are also created with that simulated reduced form. So it's a reduced form. SUR system is the reduced form. Okay, so reduced form y's are calculated, then comes from here, estimate the model, theta naught is equal to 3,1. So initialization, then estimate theta with optimization using Newton-Raphson. Then compute OLS, x1, y1, alpha 2, x2, y2, alpha 3, x3, y3. Fine. Alpha is and alpha OLS, these are the alpha OLS, and just simply compare them. Compute residuals at optimal parameters, theta 1, theta 2, theta 3, and compute residuals. So with A we need to, with loop we are simulating the residual for I is equal to 1 to t. Okay, and omega hat. So that is the residual omega hat and omega. Now we are comparing omega hat and omega. Very simple. Okay, swimming and related regression. We just did simulate data. We just did log likelihood function. We called them and we estimated beta hat and omega hat for OLS and with maximum likelihood estimation. That's all. There's nothing very different and very easy. Okay, we're done with that, and the final one is, we're not gonna do Taylor. We'll probably have a look into not Taylor, Klein's macroeconomic model. So Taylor not needed. Let's have a look into Klein's macroeconomic model. The data file contains 22 annual observations where we have consumption, profit, private wage, government wage, investment, capital stock, demand, blah blah blah. This is the model where the disturbance vector is distributed. Estimate each of the three structural equations by OLS. Three structural equations by OLS. Instrument model by IV using the following instruments for each equation. Instrumental variable, okay, because they have some commonality, I guess. These are the instruments. My god, so many instruments. Is the three identity to express the three structural variable with FIML test joins restriction. Let's see how difficult it is. First, local function, log likelihood function. Okay, so many parameters indeed. So beta will be big, alpha will be big. There's nothing very what should I say, very interesting here. Same thing, define beta and alpha, construct residual, just for the equation, construct residual, construct omega, construct residual, construct omega, construct the residual with loop, construct omega, then do the log likelihood function using the constructed residual, using the constructed omega, because you needed u for omega. That's all. Instrumental variable, as well as we have already done this equation. Then standard error of regression, then variance covariance matrix. Okay, we have already done this. So these are the local functions. Then we see how do we go through. We just t equals 22, we load data, read table, load the data, estimate consumption function by OLS, not a big deal. To end rows first, not the first one, because it's yt minus 1 we are talking about. Estimating consumption function by OLS. Okay, estimate investment function by OLS, t minus 2 to end I p t 1 n minus 1 k lag. It's just the equation. 2 to end obviously, because 2 to end is because lag. 2 to end 2 to end p 2 to end, you have to understand 2 to end, right? p w g w, that's fine, that's all. Rest are all instrumental variable. Replication, then p minus 1 because 2 to end doesn't take in R, we do. You see, for in case of y it was ct minus 1, except for the first one. X is equal to p2 to end is p minus 1, that means 2 to end minus length of p minus 1 n minus 1. This is, if you remove the first row, p minus 1. If you, this is column bind, nothing else. If you remove the last row, it is minus length of p. You are removing the first row, so p minus 1. That's all, very simple. Create a table, wage function by OLS, again same thing. Replicate first row, last row, first row. Wage function, define the what the system. Okay, estimate consumption function by IV. If you just call IV, it will automatically run. Same thing, there's no big deal here, everything is just repeatingly happening. There you go. B is equal to, we have already calculated everything, just put everything in. Oh, then FIML, after this is very manual, then FIML is with the function, then put the theta values here. That's all. It's a very simple problem. Okay, if you need to look into it more, you can email me and I can share the code with you. But this is repeating, there's no point explaining. Here I complete the chapter. Thank you very much.